we're going to model a few problems and see that we'll have quadratic equations that we can use to solve. Take a moment to read the question. Here what we have are two cars heading in different directions. One car going north, one car going west. Now, after some time, those cars are 100 miles apart. By drawing this little diagram, we see that we now have a triangle. So if we have a car going west and we have a car going north, well, the north car is 20 miles further than the west car. So we have these expressions to represent the sides of the triangle. And since we're dealing with a right triangle, we can use our Pythagorean theorem. Substitute the values in for the side lengths. And now that we have our quadratic in one variable, we can go ahead and use quadratic formula or factoring to solve. But first we need to get it in standard form. We expand w plus 20 squared to give us w squared plus 40w plus 400. And we have 10,000 on the right. Combine like terms. And this one's actually pretty easy to factor. When we factor out the GCF, we find we have a product of negative 4,800, but we need a sum of 20. So it factors to be positive 80, negative 60. Set our factors equal to 0. So the westward car either traveled negative 80 miles or positive 60. We can ignore the negative, so we know the west car went 60 miles and the north car went 20 miles more, which was 80 miles. Next, we'll start out with our rectangular pool with dimensions 20 by 30. Gardener wants to plant a strip of grass all the way around the edge, which gives us another larger rectangle. Where dimensions we're not sure, but we do know that we want all of the side lengths, or all the distances or widths, to be the same. Since we don't know what the width is, but they all have to be the same, we can use the same variable to represent that width. So conceptually with this type of problem, what we're looking at is we have two rectangles. We have the large rectangle, we have the pool rectangle, and then if we go ahead and we subtract those from each other, we get the area of the strip of grass. A large rectangle less the smaller rectangle gives us just this strip of grass going around the length of the pool. And given that we have the length and width of the pool, we also have the area that the strip of grass should be. All we need left is an expression that models the area of the large rectangle. And that would complete our equation. Well, we know that the large rectangle is going to be more than 30 feet because the distance here is 30. We also know that this distance is w, and this distance is also w. So the full length across will be 30 plus 2 times w. Similarly, with our length, we know that this part is 20, but here to the edge is w, and to the other edge is also w, giving us a full length of 20 plus 2w. So we can use 20 plus 2w times 30 plus 2w in order to get the area of the larger rectangle. So when we distribute and expand it out, we're left with 4w squared plus 100w plus 600. Then we have the area of the pool, which is also 600, equals the area of the strip. When we combine like terms into standard form, factor out our greatest common factor, then we can go ahead and factor set our factors equal to 0, and we get a possible width of either negative 28 feet or 3 feet. 3 feet makes the most sense. We can't have a negative distance. Here we have a projectile motion. We have a 140-foot tall building, which is our starting height, 112 feet per second initial velocity, and we have a function, s of t, that models its position at any given time. We want to find when, so we're solving for t, the object hits the ground, its position. Well, the ground, in feet above the ground, is 0. So we're just solving our function for when s of t equals 0. When we factor out our GCF, we find that we have the following quadratic. However, this quadratic is not factorable. Therefore, we have to use our quadratic formula. Negative b plus or minus the square root b squared minus 4ac all over 2a, which simplifies to 7 plus or minus 85 over 2. Now, because these are irrational solutions, we're going to need to round our value. This is exact, but we need to get a rounded value. So we're going to go ahead and evaluate both of these equations and see which one makes the most sense. 7 plus the square root of 85 divided by 2 is approximately 8.1, while if we subtract the square root of 85, we get approximately negative 1.1. Again, we can't have negative time, so we're going to consider only the positive answer. Last function we're looking at, we have a function f of x that models the number of company bankruptcy filings, where x is the number of years since 1990. Here we want to use the model to approximate the number of company bankruptcy filings, which means we're solving for f of x given a year of 1995, which is 5 years after 1990. So we're going to evaluate the function. No quadratic formula, no factoring, just simple evaluating with an input, which gives us approximately 74.25, which will round up or round down to the nearest whole number of filings, 74. Here, we want to solve for the year, for x, which means that 150 is the value of f of x. So we set our equation equal to 150, standard form, and then because we have decimals, we're going to need to use our quadratic formula. Negative b plus or minus the square root of b squared minus 4ac over 2a. Be very careful when evaluating the quadratic formula. The discriminant could also be very tricky. But when we do successfully simplify, we get 28.6 plus and minus the square root 1047.12 over 6.74, which then again, we're going to go ahead and do the plus and the minus. We end up getting 9.04 or some negative answer, which we know we can ignore. So 9.4 years after 1990 means it was in the year 1990.